So this morning we're going to take a look at graphing rational functions. Now rational functions, these are functions that are ratios, and for us will be ratios of polynomials. So if a polynomial p of x divided by a polynomial q of x. And graphing these things, we're going to pretty much graph them the same way we graphed any other function. We're going to look for x-intercepts and we're going to look for y-intercepts. Now, the thing is, and we're also going to look for end behavior, just like we do with polynomials. But there's a thing here. There's two other things that these bring in. So first off, we'll have our y-intercepts. We'll have our x-intercepts. But what's outstanding about, and then we'll have test points too. But what's outstanding about these, it has to do sometimes a little bit with end behavior. We're going to have what are called asymptotes. Now we have what's vertical asymptotes. And horizontal asymptotes. And I'll abbreviate vertical asymptotes as VA. And then we have horizontal or oblique asymptotes. And these last two, I'll abbreviate these as HA, OA. These here, this is what's going to be new. And vertical asymptotes basically are where we get divisions by 0. And I should put a little caveat here. We also have what goes along with these are holes. Holes and vertical asymptotes are the same thing. It's where we get a division by 0 or a potential division by 0. So what that means for our function, they occur at values of x where q of x equals 0. Now, horizontal asymptotes, oblique asymptotes, this is where we're talking about end behavior. So as x goes way down on the positive x-axis, or if we go way down on the negative x-axis, what does this rational function do? And it'll typically do one of three things. It'll sort of slowly act like a line. It might slowly act like a line with some kind of an incline. Or in some cases, it might follow some other kind of shape. But that happens when we look at large values of x, whether they're largely positive or largely negative. So let's take a look at some of these. We'll review some of these ideas and then jump into the new ones. So first off, the y-intercept. Y-intercepts, what we do here is we let x equal 0, and we solve for y. And what we're doing here is we replace y, or we replace f of x with y. So we'll do this first. Replace your f of x with y, and then solve for y when x is equal to 0. Or what you get is something like this. 0, f of 0. And that's your y-intercept. Now, for x-intercepts, since we're dealing with polynomials, we might get more than one x-intercept. That's always a possibility. So what we do here, we let y equal 0. And again, we make that replacement, we change f of x to y, then let y equal 0, and then we solve for x. And so what we end up doing is we're solving this equation. We end up getting this. 0 equals p of x over q of x. And we solve for x. And typically what happens here, if you multiply both sides by q of x, what you end up getting is 0 is p of x. And then we solve for x. Now again, p of x is a polynomial. And so as we've seen with polynomials, they could have multiple values of x that satisfy this equation. So that means we get multiple x-intercepts. So we could get, say, our first x-intercept, then a second x-intercept, and so on. So that's our x-intercept. And then we can use test points. And we're going to use test points very specifically when we try to graph these rational functions. Specifically meaning we're going to look at test points between x-intercepts and vertical asymptotes or holes. And then we're going to look at test points sort of outside of all of this, when we're sort of beyond all the x-intercepts and vertical asymptotes on the positive side and beyond all that on the negative side. I'll show you when we get there. So let's talk about vertical asymptotes or holes. Now, these occur wherever the denominator is 0. So when I talk about where, we mean x values. They occur at x values that cause that to happen. So what these look like, you've encountered these before. So for example, if you look at f of x equals 1 over x, you do get a vertical asymptote with this function. Well, here q of x is just x. So this is 0 when x is 0. So at 0, we're going to have this sort of vertical line that we imagine. Now, usually when you graph these, you don't include that line, but sometimes people do. And you get this kind of a graph. The key thing here is our branches of our function, they never can cross over that vertical line. Like they never have a value at x equals 0. You just have a branch, and then suddenly on the other side you have another branch. But you'll never have a line actually crossing over it. So this is kind of a place the function never goes. So that's an idea of a vertical asymptote. You also encounter them, say, in other functions as well. Let's see, if you look at the logarithm of x, it also has a vertical asymptote at x equals 0. And once again, this function, as it drops down, will get closer and closer to this vertical line, this dashed line, but it never quite gets there. It's always just short, just a little bit away from it. So that's the idea of vertical asymptotes. And these are boundaries that the function cannot just pass over. It can maybe be on this side and then suddenly appear on this side like a quantum leap, but it can't actually drive over it, so to speak. All right. So that's the idea of a vertical asymptote. Now a hole is the same idea, except there's a little bit extra with a hole. So for a hole, there's a point missing from the curve. So a hole might look something like this. Say this is our graph. And we might have our function here. And there's going to be a hole where there's some point missing. Let's say it's missing at x equals 2. So what causes a hole? Well, it's the same thing that causes a vertical asymptote. You get a division by 0. So a function here we might have, let's say we have this. So if we look at the denominator, if x is equal to 2, you get 2 minus 2. Well, that's 0, and that means you get division by 0. So at 2, we have a division by 0. But this is where you get a hole instead of a vertical asymptote. You notice there's an x minus 2 up here and an x minus 2 down here. Well, that would certainly suggest that there's cancellation. So what we end up getting in here, let me check my graph here. My graph here is not completely accurate. What this would actually look like is more like this. There we go. There's an accurate representation. And this is why it is. When you cancel these, you just get x. So when we graph these types of functions, if we cancel whatever is cancelable, well, this is what we actually graph. This is that function y equals x passing through the origin, not passing through here. But, and here's the thing, we never forget the original form of this function. We just don't. And the original form says, well, wait a minute, you've got an x minus 2 in the denominator. And that is 0 when x equals 2. So that means you're going to get a hole here at x equals 2. Now, when we actually graph the function, though, we go through with the cancellation, and then we graph what's left over after canceling. So that's why we have this y equals x. But when we talk about the domain, when we talk about whether there are holes, we refer back to the original function before we did any canceling. And this x minus 2 says there's a hole at x equals 2. So when these cancel, the thing that goes to 0 cancels, that's when you get a hole. When it doesn't cancel, that's when you get that vertical line, the vertical asymptote. All right. So those are vertical asymptotes and those are holes. Let's take a look at horizontal asymptotes and oblique asymptotes. So these are totally different. Now, with a hole, it's a hole in the function. The point's missing. With a vertical asymptote, the function can't actually cross over that. It can just sort of magically appear on either side, but it has to stay away from it. It can't actually have a value on that vertical line. Horizontal asymptotes, oblique asymptotes, it's different. So f of x can cross over these. Now, vertical asymptotes and holes occur where you have numbers that can't be part of the domain. You're not able to actually have a value of f of x at that location of the vertical asymptote. You can't have a value of f of x at that location of the hole. These aren't like this at all. They're totally different. What's going on here is a very different type of process. What this describes is what f of x does as basically x gets larger. X goes to infinity, or x goes to negative infinity. As x gets massively big in the positive direction or in the negative direction. And again, actually, we technically consider negative numbers very small in terms of how we order things. But the more negative x becomes, the more positive x becomes, what does f of x do? What is it going to do? And you've seen this kind of thing before. A good example, again, is f of x equals 1 over x. Now, in this case, it has a horizontal asymptote along the x-axis. And so what ends up happening, excuse me, is as this function, as x gets bigger and bigger, the function gets closer and closer to that x-axis. It just follows along. Now, in this case, it doesn't cross over, but there are horizontal asymptotes that functions do cross. Of course, the other branch does something like this. As x goes farther down the negative x-axis, it gets closer and closer to that line. Anyway, so that's the idea of a horizontal asymptote. Now, we have several scenarios, but there's 3 that we typically focus on for horizontal asymptotes and oblique asymptotes. Remember, f of x is p of x. It's p of x over q of x. So we're going to look at 3 scenarios. The first off, when the degree of p of x, a top polynomial, is less than the degree of q of x. So something like this might be, for example, f of x equals x over x squared plus 1. Here, p of x has a degree 1, q of x has degree 2. For this type of situation, we have a horizontal asymptote. So it's a horizontal line the function settles upon ultimately. And that's always going to be y equals 0. So keep that one in mind. The other scenario is when the degree of p of x equals the degree of q of x. So something like this. When we have something like this, where you say, for example, we have a degree 2 polynomial over a degree 2 polynomial, in this case, the horizontal asymptote will be y equals the lead coefficient of p of x over the lead coefficient of q of x. Now remember what the lead coefficient is. Polynomials are sums and differences of terms. Like we have 1, 2, 3 terms. And each term has its own degree. This is a degree 2, this is a degree 1, and that's a degree 0. The lead term has the highest degree. So 3x squared, because it has a degree 2, this would be the lead term for this polynomial. Then the coefficient of that lead term, that's the lead coefficient. So for this example, our horizontal asymptote would be 3 over 2, because this is the lead coefficient of the lead term for that polynomial. So you have a horizontal asymptote of 3/2. Finally, the last scenario we consider, though there are problems you're going to see in the text, at least there's a couple that suggest a fourth. But the third is degree p of x less than, I'm sorry, not less than, equal to degree q of x plus 1. So what this would look like would be f of x equals, let's say, x cubed plus x squared plus x plus 1 over x squared minus x plus 1. Where this polynomial is a degree 3, and this is a degree 2. So q of x would be degree 2 plus 1. So 2 plus 1 would equal the degree of p of x, which in this case is degree 3. Now, for this, it can get a little complicated. And let me do a different example just because the division will go easier. But let's say we have f of x equals x squared plus x plus 1, and then we have x minus 2, something like this. Well, what we're going to do is this. This is where we get the oblique asymptote. We're going to have a line that has some kind of a slope to it. Not that horizontal line that has a slope of 0, and it could be located at y equals 0 or some y equals the ratio of lead coefficients. In this third scenario, what we're going to do is we're going to divide. We divide p of x by q of x. And what we'll get, the result is a line. After, because we might also get a remainder. So the result's going to be a line plus some kind of remainder. And if there's a remainder, and if there happens to be one, we're going to ignore it. We're just going to go with the line. And there's a reason for that, and I'll talk about that in a little bit. So to explain what's going on, let's do this division. So let's say we want to find the vertical asymptote, I'm sorry, the oblique asymptote for this rational function. Well, we can divide this by this, and let's use synthetic division just because it's really fast. So we have a subtract 2, we get a plus 2. Coefficient 1, constant term 1. Bring down that lead coefficient, and then we do our process. 2 times 1 is 2. Add them, we get 3. 2 times 3 is 6. We add these, we get 7. So this is the remainder term, this is the constant term, and this is the coefficient for x. So the answer we get is this: x plus 3, remainder 7, or x plus 3 plus 7, because it's a positive 7, and we always write it under the divisor, which was originally x minus 2. Now remember with synthetic division, when your divisor is minus 2, you get a positive 2. If this was x plus 2, this would be a minus 2 up here. So this is what we get for our oblique asymptote. This is the part that's the line. And this part is the remainder. So if we're graphing this function, we're going to make sure that we have an oblique asymptote going through here. And then what happens as x gets bigger and bigger, our function is going to get closer to this line and start following it. So as x goes to positive infinity, our function is going to follow this line in that direction, get closer to it. As x goes to negative infinity, our function is going to get closer to this part of the line and then follow it. And they could cross the line, you know, if there's branches here, the function could cross this line. And we'll actually look at points where that happens, part of our test points. Now, I mentioned that we just ignore the remainder. We just throw that off and we just look at x plus 3. And here, let me add a little more to my illustration here. So this would be an oblique asymptote of x plus 3. And then this part, we just ignore. So our oblique asymptote is just x plus 3. Now this seems kind of easy. Like, why do we just get to ignore that? Well, horizontal asymptotes and oblique asymptotes, they're really a kind of end behavior. It's what happens when x goes way down the positive x-axis or it goes way down the negative x-axis. It's end behavior. And here's the thing. When x is kind of small, this term can be massively influential. So let's say we let x equal 1. So we have 1 plus 3 plus 7 over x minus 2. Let's make it a little easier. Let's make it 0. Let's let x be 0. So what we get is, we simplify this down, and this is for the oblique asymptote. We'll get 3 plus 7 over negative 2. And so it looks like we're going to have a value of 3, but guess what? This is negative 3.5. So at x is 0, this remainder term is dominant. This negative 3.5 is going to knock out this 0 plus 3 that the line part came up with. So the line part has 0 plus 3 is 3, but the remainder term is going to give us this negative 3.5, and so we get negative 0.5. So that remainder term is fairly, well, it's really affecting the line part. In fact, here it wiped out the 3 and still had some negative number to go. So it doesn't seem like you can ignore this remainder. Well, we ignore it for this reason. Its end behavior is what the horizontal asymptote and the oblique asymptote describe for us. And that's why we use them. So what happens if we let x be 1,000,000? So this was actually for x equals 0. So if x is 0, we got negative 0.5. Now for x is 1,000,000, we get 1,000,000 plus 3 plus 7 over 1,000,000 minus 2. So the line part, the x plus 3, this becomes 1,000,003. But this over here, this practically, the remainder part practically disappears. Let me grab a calculator and let me show you. A little more exact answer for that calculator. Pardon me just a moment. All right. My calculator's rounding off a little bit too much. Now, approximately, you get something like this. The point is this. Now the remainder is very small, the remainder term. It's contributing hardly anything to the x term. And so this becomes, for all practical purposes, just 1,000,003. We can ignore the large values of x, the remainder term. When we're close to, say, x is 0, the remainder term is very influential. Remember what we had. The line term, when x was 0, was 3, and this was negative 3.5 to give us a negative 0.5. So the remainder term is very significant for small values of x, or values of x, I should say, closer to 0. But as we get farther away from 0, instead of giving a line term like this and a remainder term like this, where the remainder term is significant, here the line term is massive. The remainder term is practically 0, and we can pretty much ignore it. And so that's why we drop the remainder term. We're only interested in horizontal asymptotes and oblique asymptotes when we're dealing with values of x far away from 0, whether they're far in the positive direction or far in the negative direction. For x values close to 0, we're going to use the same skills that we've used when graphing other functions. Y-intercepts, x-intercepts. Of course, we now have this new thing with horizontal asymptotes and holes. And then we're going to use test points. And we usually choose these between x-intercepts and vertical asymptotes. They tell us what's going on around these structures. And so we can see, well, where is our function? Do we have something like this? Let me make this a vertical asymptote. We might see what's happening at x is 1 and x is -1 to see if we have this kind of a function, or if we have this kind of a function. So plugging in x is 1, seeing what kind of y value we get. Plugging in x is -1, seeing what kind of y value we get. It will help us decide if we have a function like this or a function like that. And we want to do this on either side of the vertical asymptotes. Now, we also do this kind of at the end. I'm going to abbreviate test points as TPs. We'll look at TPs on far sides of x-axis. So what does this mean? Well, let's say we have some intercepts and vertical asymptotes. So we could have, say, a vertical asymptote here. So here's an x-intercept, another x-intercept, another vertical asymptote. We'll just leave it like that. What we're going to typically do is between the x-intercepts and the vertical asymptotes, we'll look for a TP. So we'll look for TPs between intercepts and asymptotes. We'll also look for TPs on the far sides of the x-axis. So out here, we'll choose a TP, kind of beyond everything. And then out here, we'll choose a TP. And so those are the two times we're going to look at test points. Between the intercepts and the asymptotes. So we got those right there. And then on the far sides of, well, everything that's going on. So that's what we're going to follow. So, for example, let's take a look at this. And let's say we have 4x squared over x squared minus 9. So first off, let's look for the y-intercept. Well, this is when x is 0. So we're going to look at f of 0 equals 4 times 0 squared. And you have 0 squared minus 9. And this is 4 times 0 squared. It's now 40. And remember, we want to replace this with y. So we have y equals 4 times 0 squared over 0 squared minus 9. So we get 0 over minus 9, or 0. So when x is equal to 0, y is equal to 0. So there's the y-intercept. When we have an x of 0, we get a y of 0. Now for the x-intercept. Here we let y equal 0. We're going to solve for x. So we have our y equals 4x squared. We have x squared minus 9. We're going to let y be 0. So 0 is 4x squared, x squared minus 9. And to do this, we can multiply both sides by x squared minus 9. This will be 0. 0 is 4x squared. Divide both sides by 4. Square root of 0 is just 0. There's no plus or minus 0. You see that x is equal to 0. So when we let y be 0, get an x of 0. And so what you discover is that our x-intercept and y-intercept, they're the same point. They're the origin. So keep that in mind. All right. So we found out that our y-intercept and our x-intercept are the origin. So the function passes through the origin. Well, now let's take a look at some vertical asymptotes or holes. So for the vertical asymptotes or holes, we look at q of x. And that bottom polynomial was x squared minus 9. So if we factor this out, this is actually x plus 3, x minus 3. This is the difference of squares. If we set this equal to 0, if you want to find where q of x is equal to 0, well, where does that happen? Well, it happens when x is negative 3, because negative 3 plus 3 would be 0, and then over here when x is 3. So we have q of x equal to 0 for x is negative 3 and x is 3. Now, is this a hole or is it vertical asymptotes? If we look at our function, do these factors cancel out? Well, they don't. There's no x plus 3 up here. There's no x minus 3. So these don't cancel out. So that means we're not going to have holes. We're going to have vertical asymptotes. So you have a vertical line at negative 3 that the function cannot cross. A vertical line at positive 3 that the x equals positive 3 that the function cannot cross. So let's look at, do we have a horizontal asymptote or an oblique asymptote? Well, this is what we've got. F of x, sorry, P of x over Q of x is 4x squared over x x squared minus 9. Now what we see is this. The degree of p of x is 2, which is also the degree of q of x. So these have the same degree. Now when that happens, it's our second scenario, and that's horizontal asymptote. And it's the ratio of the lead coefficients. This one just has one term, and that's the lead term, and its coefficient is that visible 1. So we get y equals 4. So y equals 4 will be our horizontal asymptote. All right. So let's put all of this together. Now we're still not done. We still need to look at test points, but let's see what we have so far. We found out the x-intercept and the y-intercept is the same point at the origin. We found out that we have vertical asymptotes at x equals 3 and x is negative 3. And that we have a horizontal asymptote of y equals 4. So now we need to look at test points. So what we do is let's choose some test points between the vertical asymptotes and the intercept here, this x-intercept, which also is the y-intercept, but just the nature of the function. So let's say we have a TP, test point, and let's choose negative 1. Let's choose that a little more accurately, more like over here. Negative 1. And then we'll do a test point of 1. So that's between the vertical asymptotes and the x-intercept. And then out here, let's say do a TP of 4 and a TP of negative 4. Finally, there is something we're going to do at the end here. It's kind of like the test point procedure, but we want to find out if the function crosses y equals 4. And we'll do that at the end. Now, functions cannot cross vertical asymptotes, but they can cross horizontal asymptotes and oblique asymptotes. So let's look at these test points. So what happens is this. F of negative 4. That's 4 times negative 4 squared over negative 4 squared minus 9. Squaring this gets rid of the negative, so you get 16 times 4, that's 64. And then let's see here, 16 minus 9 is 7. And 64 divided by 7, let's use a calculator to do this quickly, and 9.14. So the moral of the story is this. This is y equals 4. At negative 4, we're up here. The value of 9.4. Now this isn't going to be exactly drawn on the scale. There's our 9.4 up here. So this isn't drawn on the scale 4, and then that doesn't seem quite right. And it isn't. But what's going to be important for us is we know that this point is above the horizontal asymptote. That's really the key thing. Same thing with this. Put in 4. Going to get the same thing. So again, on this side, we're also above that horizontal asymptote. Now for -1, let's see, f of -1. Well, this will just turn out to be 4 over 4 minus 9, or -4/5. So the key thing here, -4/5, excuse me. And this isn't drawn on the scale. It's right about there. The key thing here, our function seems to be below the x-axis. Now let's try f of 1. We're going to get the same thing. Oh dear, I'm sorry, I made an arithmetic error. It's 1 -8/8, which is -1/2. I'm sorry, I made an error there. It's -1/2. I'll give you a second there to update your notes. 1 minus 9 is 8, -8. So technically what you get is this. And then positive divided by negative is -1/2. So we make sure that's -1/2. Again, nothing here is drawn on the scale, but the main thing is we're below the x-axis. The same thing here. This is going to be 1 minus 9, 4 over -8. Positive divided by negative is a negative. And so once again, we're down here. So we've done this with our test points. Now what's significant about this? Remember, there's only one x-intercept. It's that right there. So that means there's no other place along the x-axis where this function crosses it. So if this function is below the x-axis in this area, it's going to stay below the x-axis in this entire area. And the reason is, this is the only place where there's an x-intercept. That means it's the only place where the function can cross the x-axis. So if it's not crossing the x-axis here, it's not crossing it anywhere else. So that means this tells us our function is probably doing something roughly like this. And then it's going to dive down and follow these vertical asymptotes, though it'll never quite reach them. And if you're a little concerned that, well, maybe it does something like this, but then dives down, well, again, you can use more test points over here to verify. But for the problems we have in the text here, that's really not something we're going to have to worry about for the most part. Now, same situation here. This is not going to cross the vertical asymptote, so it could be doing something like this, going up. But it could cross the horizontal asymptote, and perhaps I'm being a little over-optimistic. Well, maybe it does something like that, crosses the horizontal asymptote. So we want to test to see if that's true. So our function, f of x, is 4x squared over x squared minus 9. So if this does cross the value, if it crosses the horizontal line y equals 4, that means f of x must become 4 at some point. So let's solve for x. If this is true, we don't actually know if this is possible. If we do cross the horizontal asymptote, where? What value of x does this happen? Well, we multiply by x squared minus 9. A real kind of trick here is try to get rid of the denominator, just like we did with linear functions that had fractions for coefficients. Get rid of these denominators. So we multiply both sides by x squared minus 9. Those will cancel. And so what we'll get is we distribute both terms. We get 4x squared minus 36 equals 4x squared. Subtract 4x squared from both sides. And we're starting to see this isn't going to work. What we'll end up getting is negative 36 is equal to 0. And what that means, that's of course not possible. So that means the only way for 4 to equal f of x is to have negative 36 equals 0, which is impossible. So that means this does not cross the horizontal asymptote. So it probably means we're going to do something like this. We'll follow the vertical asymptote, we'll follow the horizontal asymptote. Let me draw this a little better, a little better scaling here. So what we end up getting are vertical asymptotes. There's our x-intercept. Here's the horizontal asymptote. We're doing something like this here, where we contact the x-intercept, and then that's it. And then up here, we don't cross the vertical or the horizontal asymptote. We do something like this. Same here. And so this that's going to be roughly a rough sketch of what's going on. All right. So that's it. I'll do some more examples. I'll post some examples separately, but that's the main idea with working with these. And if you have any questions, let me know.